So last time we left off talking about Fourier series, how we could use Fourier series to represent a periodic function, and I gave you some examples, some common examples of periodic functions. We could look at a test for if it's periodic. The test would be if the function is equal to the function at the same time plus or minus n times the period t, where of course the little t, that's time, and the large T is period. Okay, so that would be the function. If that's true, it's a periodic function, and you can, if it passes some other tests, a test we'll talk about, you could definitely do it with Fourier series. Fourier, as I mentioned last time, was named after Jean-Baptiste Joseph Fourier. Some people call it Fourier. It's probably a little more common, Fourier, but that's, I guess, tomato, tomato. You can break that up however you want to. He was a French mathematician, lived from about the mid-1700s to about 1830. And I think I mentioned last time that it was for his work in heat transfer. And you could see that heat transfer, that could be periodic also. If you were to look at heating and cooling, maybe in a desert as the temperature goes up or down, definitely a periodic function. We see this a lot in electrical, and I think we'll just spend one day on this. That'll get us set up nicely to begin our work next term, where we'll do this in a lot more earnest sense. And then we'll spend most of next week, the last week of the term, just doing review, going back and reviewing over the entire term, preparing for the final. So let's look at some requirements. I think just to rehash very quickly what we had last time, remember some of those periodic functions that we saw. You had the fully rectified wave or the half rectified wave. You could have a square wave. I think one of them that we'll look at would be a ramp wave. These are all periodic functions that are not strictly sinusoidal, but we can use a series of sinusoids to approximate those. The rules for the sure use, and even if these rules fail, you might be able to use it. It's just not a sure thing. And the rules are not very restrictive when we look at them. There's 4 of them. The function is single valued. The function is single valued. Most things that are made with a real generator are going to be single valued. For instance, if we look at something like this kind of a sawtooth wave, that's single valued. That would be okay. Whereas if we look at something, maybe it looks like a sawtooth, but maybe more like a shark's fin, something like this is not going to be single valued. Okay, so we're not going to get involved with something like that. So that'd be a good example of one that's single valued and one that's not single valued. Anything made with a real generator is probably going to be single valued. We don't have to worry too much about that. The second one is that the function has a finite number of discontinuities. Continuities, let's see, getting going again. There we go. Finite number of discontinuities per period. I mean, you might panic initially and say, hey, that square wave's got a infinite number of discontinuities, but remember it's per period. So per period, a lot of these, I really can't think of an example that would fail this. So 3, finite number of minimum and maximum per period. Finite number, this is the number sign, right? Number sign, pound sign, not hashtag, so don't send me an email. I can't find hashtag finite or whatever. Again, per period. And I would be, you'd have to talk with a mathematician to come up with someone that could because I don't think I can think of one that fails that test. Probably the most important practical one is the fourth one. Is that the integral of the absolute value of f of t over one period exists. Okay, and that from a practical sense, we're going to be doing quite a bit of integrating. So if we can check those off, and most of the time, once we've checked and made sure it's periodic, those other rules are not a problem. But I just want to lay them out. Once we've done those, then we can say that f of t. Okay, and I'm not going to say V of t or I of t, although a lot of times we'll talk about current and voltage being represented this way, but this could really be any periodic function, is equal to a sub v plus the sum from n equals 1, 2, 3, and so on to infinity of a sub n cosine n omega naught t plus b sub n times the sine of n omega naught t. Okay? And this is actually equals. This is a perfect fit. Okay? Now, a lot of times with infinity, I always get a little nervous about infinity. Don't have time to do all of them. Usually it's a pretty good fit for stopping well short of infinity. For instance, you could stop maybe with 3 or 4 and probably recognize the shape of it. If you go to 30 or 40, which I mean pushed, you could probably do by hand. It will be very obvious. A computer, you could do 300 or 400 or 3,000 or 4,000 or 300,000 or 400,000, and you will not be able to distinguish it from the actual wave. So you really don't have to get very far out to infinity to get a pretty good fit. But if you go to infinity, this is indeed actually equal. Well, the a sub v, the a sub n, and the b sub n, those are the coefficients. And that is another name for work. That's where we'll have to do all the work in finding those. That's going to be where we spend most of our time in our task. The omega naught, that's our fundamental frequency. The fundamental frequency, and then we would say n omega naught would be the harmonics. Okay. I think you messed around with this a little bit in GE 101 just to give you something to calculate with. And I'm sorry, not GE 101, GE 103 when we were working with Excel. And if you were to look, for instance, on a square wave, so we had those harmonics. So if we looked on a square wave, the way it's going to build this square wave, for instance, it'll have the first one that's the frequency of the square wave, and then it's going to add one that's twice the frequency of the square wave, and then one higher and higher yet, and it'll continue to add those together to come up with a square wave. And when you get done, I don't know if you remember that exercise from last year, you'll end up with a square wave that has a little bit of a noise up here. It comes up about like that. Okay, you'll get something like that. You get a pretty good approximation of this thing. But you'll see that you're adding sines and cosines, that their frequencies get progressively higher because of this n times omega naught. So let's talk about calculating these coefficients, a sub v, a sub n, and b sub n, and see what those turn out to be. I think I got room here to put them at the top of this. A sub v is equal to 1 over t times the integral from t naught to t naught plus a period t. Again, lowercase t is time, uppercase t is period. And then I just put the function in here, f of t dt. And this is actually, the other ones, a sub n and b sub n, are a little harder to think about. But this one's pretty easy. This is the average value. Okay, we add them up and we divide by the period. That's the average value. So a lot of times you can probably find the average value by inspection. For instance, if you have a wave that is a ramp like this, if we look at this, if we know this value, of course we know that this one's 0, the middle is going to be the average value, isn't it? So a lot of times we might be able to avoid evaluating A sub v. A sub k, let's see. Probably, did I put them in? Yeah. We could say A sub k, or sometimes A sub n. I think I wrote them as A sub n above. That's going to be equal to 2 divided by the period t times the integral from t naught to t naught plus t of f of t times the cosine of k omega naught t dt. Or we could put n in there. Sometimes they'll use n for that. Okay. So that's A sub k or A sub n, depending on whose book you're reading. And then we could talk about B sub k or B sub n, which would be, again, 2 over the period t times the integral from t naught to t naught plus t of f of t, then sine of k omega naught t dt, where this could also be n. Okay. Questions with that? So those are those values. You can see we're probably going to be doing quite a bit of integrating. When we get involved in this next term, we're going to try and look for symmetry to make our life easier. Sometimes if we can recognize some symmetry, even wave symmetry, odd wave symmetry, and so forth, we can maybe not have to calculate all of these, but we'll just start out calculating them all. Have you done this in math class? Integration, yeah. Hopefully you've done that in math class. That's good. Okay. Have you done Fourier analysis in math class? No? Okay, good. Okay, so, well, let's just try an example then. It's probably not quite as bad as it looks. So let's try that ramp wave. We'll say that we have something like this. And it's been going on for a while. And we'll take this as some voltage. We'll say that comes up to some maximum value V sub m. I think I'm going to need a better pen before I'm done. And then this is, of course, minus period t. This would be 0, 1 period t, 2 periods, 3 periods. So we have, maybe we'll say that this is t naught right here, and that this is then t naught plus t. I mean, you could take any period that you want in there. It's probably going to be a lot easier to go from here to there rather than maybe saying that that's your period there. That would be fair too if you wanted to really punish yourself from an integral standpoint, but it's probably a little easier to take this as our period. Now, what we'd like to do is we'd like to come up with a representation of that wave, a numerical representation based on sines and cosines, a Fourier series for that representation. So the first thing I'll do is I'll probably come up with an equation for that. I could say that V of t is equal to, let's see, the rise is Vm over the run, which is going to be 1 period, t. Then I'll multiply that by t, and I will add the y-intercept to that, which is 0, right? That's really just y is equal to mx plus b, isn't it? Okay, so I come up with that equation, or more specifically the equation v of t is equal to vmt divided by the period. Okay, so I got something like that. I guess I could do the average value. We might say that the average value then is 1 over the period t times the integral. I'm going to go from 0 to t of the function, so that would be Vm divided by the period times t, and then I need a dt there, which turns out to be what? Vm over t, that's going to be a constant, isn't it? So I have Vm over t, and I have a 1 over t, and the integral from 0 to t of t dt, which gives me what? 1/2 Vm. All right. I think a lot of you probably would have predicted that. I mean, if this value is Vm up here, the average value is going to be halfway up there, isn't it? So hopefully that works. So that's our average value. Unfortunately, a sub k and a sub n, or b sub k and b sub n, that's not going to be so easy. So we'll go ahead and get started with that. Questions with the average value? Everyone's okay? Good. That's not very clear there. That looks like it's taken to the t value. Okay, so we're multiplying that by t. Okay, so let me get just started with a sub k, and I could say that that's 2 divided by the period t times the integral from 0 to t of v sub m divided by the period times t times the cosine of k omega naught t dt. Okay, so I got to integrate that, right? And we could say that that was Vm over t, that's a constant, so I've got 2 Vm divided by t squared times the integral of t, integral from 0 to t, of t cosine k omega naught t dt. And we usually don't put these parentheses in here, but I'll do it this time as we're starting out. That's in the argument of the cosine, right? Normally we just recognize that in context, but since we're just starting out, I'll make that clear. So let's see, how could we do this? You could go to a algebra system, computer algebra system, calculator, something like that. You could do a table, handbook, or table. I guess no one goes to a handbook anymore. You just go to Google, right? Okay. Next term, engineering 203. It's a little different. The test won't be multiple choice or workout. It's open book, open notes, open computer, open everything. Bring your laptops in and go for it. And I remember one time I brought in a test and I forgot to put an integral table with it. I thought, oh man, this is going to be a disaster. So I just checked real quick. I Googled it, integral table, and within the first page of Google, a pretty good table came up that had the answer to it. So I guess you got a lot of resources out there. So you look up a table, right? In my day, we used the CRC handbook, Chemical Rubber Company handbook, handbook of chemistry and physics. I got some great math tables in there. If you got a good table in the back of your math book, that's fine. I mean, if you wanted to be a real purist and you're the math type, you could do parts. Probably integration by parts, right? Isn't that how you're going to solve that thing? But that's kind of a long trip. So a variety of ways. And I'm going to then kind of gloss over it a little bit. I mean, if we were looking at a table, we'd look at the integral of x cosine ax dx, right? Isn't that what we're looking for, essentially? Okay. So however you want to proceed from there, you would end up with this, that this is equal to 2 Vm divided by t squared times 1 over k squared omega naught squared times the cosine of k omega naught t plus t divided by k omega naught sine of k omega naught t. And then we have to evaluate this thing at, what, 0 and t? So we have something like that. Let me double check that. Okay, so make a few comments on that. like I said, when we do this next term, it's that the tests are open book, open note, open computer. It's a free-for-all, which is, I mean, good and bad. You make the test quite a bit harder with that, but you kind of put you in a more real-life setting with that. For those of you that thought, oh man, I just got close to passing this class, and then I'm going to have to integrate something like this on the final in here, there actually won't be a question like this on the final. Okay, so I guess if you're a mechanical, you're lucked out. Anyway. So what's this going to look like? I got to put the upper and lower limits into this thing. Although, you know, I don't want everyone switching to mechanical. What the strengths of materials? We're going to twist things up a little bit in there. We're just going to do one midterm examination, so it's going to be a true midterm. But then we'll have weekly quizzes. And the one thing I do on weekly quizzes, they are actually write out. They're pretty short, and it's no calculators, no nothing. Okay. So I'd like you to realize how much you have up in your head, and it's not about a calculator. So that'll be a little twist. So everyone's going to have some challenges to keep them going next term. You won't get bored. So let's put these things in here. I'm going to have 1 divided by k squared omega naught squared times the cosine of k. What's omega naught? Omega was, in general, omega is 2 pi times the frequency f, right? Those of you that did lab this week probably recognize that. And then f is equal to 1 over the period t, so I could say that this was 2 pi over t, couldn't I? So I'm going to use this one here, make this substitution for omega naught, and say that I have 2 pi over t. And then when I put in the upper limit, I have t. And I will add to it, putting in the upper limit here, I get t, k, omega naught, sine k, 2 pi over t times t. Then I have to put in the lower limits, right? So I'm going to be subtracting the lower limits. I have minus 1 divided by k squared omega naught squared times the cosine of, when you put 0 in there, it's really, no matter what you have 0, don't you? And then I will have minus, when you put 0 in for that, you get 0 times sine of whatever, right? So let's look at this. What do we have here? I get to cancel those, don't I? So I have the cosine of k, which could take on the value of 1, 2, 3, 4. So sometimes I'll draw a unit circle on this thing and look at these. So if k is equal to 1, I have 2 pi. There's 2 pi there, isn't it? When a k is equal to 2, I have 4 pi, so I'm back there again, aren't I? So what's that always equal to? It's always equal to 1, isn't it? Yeah. So that's always equal to 1. What's this one always equal to? Yeah, this one's always equal to 0, isn't it? Cosine of 0, what's that always equal to? 1. Okay, and this, of course, is 0. So let's see. Keep going on this. So I've got then that a sub k is equal to 2 Vm divided by t squared times 1 over k squared omega naught squared. Then that's 0. And then I'm subtracting minus 1 over k squared omega naught squared. So what do we have then? Yeah, for all k.
Why didn't you replace
I could in here I could have, but I actually knew it was going to go away, so I didn't spend the time to do it. Well, you could certainly. Other questions? Well, you might say, well, it'd been nice to know that beforehand. Hopefully, if we recognize some symmetry and whatnot, maybe we could not have to go through that. But anyway, we've got the average value. We've got a sub k. Let's finish up with b sub k. So b sub k is going to be equal to 2 over the period t times the integral from 0 to t of Vm divided by the period t times the time times this time the sine of k omega naught t dt. Exactly the same as the previous one, except switch your cosine to sine, which will change the integral some. So if you go through the integration again, however you want to do that, I'm not going to belabor that part, whether you use a table or a calculator or go through parts. You're going to come up with 2 Vm divided by t squared. You'd factor that out. And then you're going to have 1 over k squared omega naught squared sine k omega naught t, and then minus, as you might expect, minus t over k omega naught cosine k omega naught t. This whole thing's evaluated at 0 and t. Okay, so I'll put the values in here. Let's see, I'll go ahead and say I'll have k 2 pi over t times t minus t over k omega naught cosine k 2 pi over t times t. Then I have the lower limit. I've got to subtract off the lower limit, so I have a minus 1 over k squared omega naught squared times the sine. When you put the lower limit in there, you get k omega naught 0, so it just turns out to be the sine of 0. And then, let's see, that negative and the negative for the lower limit, because we subtract the lower limit, but I already have a negative there, is going to cause this to be a positive, but that's a bit of a mute issue because of this term, because we'd argue about whether it's positive or negative 0, right? Because of putting the lower limit there. So I've got that. So now what is this thing? Again, if I look at a unit circle, so if I look at the 2 pi, when k is equal to 1, I'm at 2 pi. So the sine is 0, right? So this turns out to be 0. If I'm looking at 3 pi, or is that right? No, 6 pi. No, it'd be 4 pi. When the k goes to 2, I have 4 pi, and then I have 6 pi. So yeah, I'm always going to be there. Once in a while, you get in a situation where that alternates. So you have to be careful of that. Let's see here. Cosine. I'm always going to be back over here, right? So what's that always going to be? Should always be 1, shouldn't it? And then the sine of 0, that's 0. And of course 0 holds for that. So the only thing that I get anything out of is this middle term, isn't it? So I could say that I have 2 Vm t squared, then I'm going to have a minus t times k omega naught. Is that right? Yeah. Which I could start to work through. Put the negative sign out front, 2 Vm, then I'll have the period t, and we'll have t squared k and omega naught. I'm going to make my substitution for that. Remember that omega naught could be written as 2 pi over t. denominator of a denominator is actually a numerator, so I'm going to get to say I get to cancel this and that, right? I get to cancel the 2's, and I'm left with what? Minus Vm divided by pi times k. Okay. And that's B sub k. That's B sub k. So we've got A sub B, we've got A sub k, we've got B sub k. We can put this whole thing together. So I'm going back to our very first page here where we said, well, this all gets fit together like this. So let's see if I can. So real quick, we'll just say f of t in general is your average value plus the sum of a sub n cosine n omega naught t plus b sub n sine n omega naught t. Your author does this, and I'll stick with it. We're changing back to n now. So we could say for our particular example that v of t is equal to the average value. What do we have for the average value? That was right here, wasn't it? There's the average value, 1/2 Vm. Vm over 2 plus the summation, n equals 1, 2, 3, and so on, up to infinity of a sub n. What was a sub n? That'd be a sub k, right? Do we have an a sub k? Right here, it was 0. Good with that? Okay, so I have 0 cosine n omega naught t, obviously that goes to 0, plus b sub n. We just finished up with b sub n, that was our minus v sub m divided by pi k times the sine of n omega naught t. And I'm going to switch that. I should have done that already. I switched the k to n. There we go. So I'll tidy this up a little bit. We could say we have Vm divided by 2 plus, maybe I won't be so hasty on that plus. I think I'll take, this term goes to 0, right? So I'm just left with this term here, so I think I'll factor a few things out. First thing I think I'll factor out is a negative sign. So I'll have minus, I can take out a Vm, and then pi. And we're going to sum up from n equals 1, 2, 3, up to infinity. What do we have left? We took out the Vm and the pi. So I'll have 1 over n times the sine of n omega naught t. Okay, and that would be a exact answer. If you go to infinity, if you grab that thing and do, let's say, the first 3, I think you'll recognize a ramp or triangle wave. If you grab the computer and take the first 30 or 40, it'll begin to be hard to distinguish it from the actual wave. Now we could express it a little bit differently if we wanted to. Go ahead and say that we have Vm over 2 minus Vm pi, and I'll put an n in here. N is equal to 1 for the first one, so sine omega naught t, then minus Vm over 2 pi times the sine of 2 omega naught t, and then minus, did I get that right? I don't think I should have that 2 in there, should I? Yeah. Should just be Vm. So the first one, yeah. And the second one, yeah, 2 is in the denominator. 2, okay. Then the third one, Vm over 3 pi sine 3 omega naught t, and so on. Yeah. So this will give us quite a bit of work next term, because what we're going to do is we're going to take and we're going to put this function into a filter. So if you take this and you put it into a filter that filters out all of the higher frequencies, what's the higher frequencies? It's going to filter out those terms, right? So it'll be kind of interesting to see what we get out. Okay. So we're not only going to talk about coming up with a model for the waveform, which this definitely is, a numerical model for that waveform. We're going to talk about then maybe applying that to a filter and seeing what we get out. So we'll be able to spend lots of time on this next term. Hopefully that's good. When we get together next time, we'll spend the final weekend here going over review, just doing neutral problems, three-phase problems, and things like that. So that's where we'll go next week. Take care till then. Yes,